Guys, Assalamualaikum and salam sejahtera. In today's lecture, we continue to our next chapter, which is our chapter number 7. So this chapter is discussing about graph. Previously, the graph that we know have a form, for example, like this. Okay, the graph. Also, the graph in the form of like this. Alright, there are a variety of graph that we know before this. So in discrete mathematics, we have different kind of graph. Because in discrete mathematics, basically graphs are discrete structures consisting of vertices. And edges that connect these vertices. Okay, if you have a single, for singular, we call it as vertex. Okay, if you have more than one vertex, we call them as vertices, and the line that connecting these vertices we call as edges. All right. So there are different kind of graphs depending on whether edges have directions or not, whether multiple edges can connect the same pair of vertices or not, and whether loops are allowed or disallowed. So it depends on the condition we can categorize the different kind of graphs. So the application of graphs, there are a lot of application of graph. Okay, so graph can be used to illustrate and also can be used to model variety of areas. I'll give you some example. Graph can be used to represent the competition of different species in an ecological niche. Okay, other than that, graph also can be used to represent who influences whom in an organization. Graph also can be used to represent the outcomes of Robin Round tournaments, etc. Okay, other than representing something, so graph also can be used to model. For example, model acquaintanceship between people, can be used to model links between websites, and graph also can be used to model telephone calls between telephone numbers, etc. So there are a lot of application of graph in our real life application. So the model that we obtain by using graph can be used to, for example, first to determine whether it is possible to walk down all the streets in a city without going down a street twice. That is the first application. The second application is we can use the model of graph to find the number of colors needed to color the regions on a map. The model that we obtain from graphs also can be used to determine whether a circuit can be implemented on a planar circuit board. And also the model can be used to determine whether two computers are connected by a communication link using graph model or computer networks, etc. So from the model we can apply in variety of area. Okay, that's how useful the graph is. Okay, now I give you the proper definition of graph. So in discrete mathematics, we define the graph as given in the definition number 1. Suppose we are given V, which is a non-empty set. So again, we are playing with set. So V is a non-empty set of vertices, and E be a set of edges. That means we have two different sets. The first set is V, denoted by capital V, which contains the vertices. Right? Suppose in this figure we have 4 vertices. We have A, we have B, we have C, and we have D as the vertices. For singular we call it as vertex. For example, A, we call it as vertex A. So more than one vertex we call them as vertices. Alright, the second set is E. So the set E is consisting all the edges connecting these vertices. Alright, for example, let's say we denote the edge as E1, for example, E1, E2, E3. So the set E contains, we have E1, okay, we have E2, and so on until we cover all the edges that connecting all the vertices in this particular graph. So the combination of these two sets, V and E, we put together in single parenthesis All right, so it is the notation for the graph G. Okay, graph G is denoted by capital G equal to the in parentheses we have two sets V and E. So that is graph. Okay, that is graph, which is a collection of vertices and edges. Each edge has either one or two vertices connected with it. Okay, edges, each edge has either one or two vertices associated with it. We call them as endpoints. For example, for the edge E3, so E3 we have vertex B and vertex D. All right, so we have vertex B and vertex D as the endpoints because the edge E3 connecting the vertex B and vertex D. So these two vertices we call them as endpoints of the edge E3. An edge is said to connect its endpoints. All right. Okay, if the set V, which contains all the vertices, okay, is an infinite set, as you can see here, we have triple dot here, so that means there are infinitely many vertices in this set. Or the edge, which is another set in the graph, is an infinite set. Then automatically we can say that the graph G is an infinite graph. So that means anyone, either V or E is infinite, then we can say that the graph G is infinite. Right? If both sets V and E are finite sets, that means there are finitely many vertices and finitely many edges. Okay, as you can see, there are M vertices, that means it is finite. We also have N edges, that means it is finite set. So if we have these two finite sets V and E, then the graph G is called as a finite graph. Based on the order of vertices, graph can be broadly categorized as directed graph or undirected graph. As I mentioned before, based on some conditions, we can categorize graph. So if the condition is regarding the order of vertices, okay, the order of vertices, which one is come first, which one is comes later. So based on this category or based on this condition, graph can be broadly categorized into two main classes. The first class is called as directed graph, and the second one is called as undirected graph. In undirected graph, the order of the vertices does not matter. Doesn't matter which one is come first, which one comes later, doesn't matter. Okay, that's for undirected graph. Okay, on the contrary, for the directed graph, the order of these vertices does matter. In other words, the order of vertices in directed graph are important. Okay, it's important. It's matter to consider which vertex is come first and which vertex is comes later, because it determines the direction of the arrow. Because in arrow we have tail and head, so this order will determines determines the direction of arrows from one vertex to another vertex. That's why the order does matter in the directed graph. Now we move to the definition number 2, a directed graph. Okay, so this definition is regarding the directed graph. A directed graph, or also sometimes called as a digraph, which is G equal to VE, okay, consists of a non-empty set of vertices V and a set of directed edges. The first one is similar, just like the ordinary graph, okay, consisting a set of non-empty set of vertices. But for the edges, for the directed graph, the set E is a set of directed edges, or sometimes called as arcs. Okay, can be denoted by E prime to distinguish between E and the ordinary E and also the directed E edges. Each directed edge is associated with an ordered pair. Ordered pair, that means the order matter of vertices. Okay, each directed edge is associated with an ordered pair of vertices. The directed edge associated with the ordered pair, we have U and V. Okay, this is an ordered pair as we learned in the relation chapter. Okay, U and V, the orders matter. So it's said to start at U. That's why U come first, and end at V. That's why V comes later. Okay, the order is important because from the order we can know which one comes first and which one comes later. Which point is the starting point and which one is the ending point. So from parenthesis UV, we know that it starts from U and ended at V. Okay, definition number 3. Two vertices U and V in an undirected graph. Undirected graph G are called adjacent. Okay, two vertices U and V in an undirected graph G are called adjacent in G if U and V are endpoints of an edge E of G. Alright, so in undirected graph, that means the order of vertices doesn't matter. Okay, so we have U, we also have V vertex V. Okay, so if this vertices connected by edge E, okay, in the undirected graph G, so we call that, okay, U and V are called adjacent in G. U and V are adjacent in G. Such an edge which connecting U and V is called incident. The edge E is called incident with the vertices U and V. Okay, such an edge E which connecting U and V is called incident with the vertices U and V. So the edge E is also said to connect U and V. Okay, class. So in this chapter, we are dealing with a lot of definition actually. Because we need to understand a lot of terminology. Okay, so you need to understand about adjacent, incident, and so on. So please pay attention at the definition. Alright, you need to understand what is adjacent, what is incident. There are a lot of terminologies, important terminologies that you need to understand in this chapter. Alright, so we have adjacent in G, that means U and V are connected together in G. So we call them as adjacent in G. And then the edge E which connecting U and V, we call this edge as incident with the vertices U and V because it connecting U and V. So the edge E is also said to connect U and V. Alright. To describe the set of vertices adjacent to a particular vertex of A. Okay. To describe the set of vertices adjacent to a particular vertex of a graph, consider the following definition. The set of all adjacent of a vertex V of G, okay, so the vertex V belongs to the graph G, is called the neighborhood of V, denoted as NV, means neighborhood of the vertex V. Okay, this NV is a set. It is a set. So this set contains all vertices connected to V. Okay, it is a set. That's why we need to use the curly parenthesis. It contains all the other vertices in the graph G that connected to V. Alright, so if A is a subset of V, A is a subset of V, the set of all vertices in G that are adjacent to at least one vertex in A is called as, is denoted as NA, neighborhood of the subset A. So, the neighborhood of the subset A is equal to the union of all NV for all V in A. Okay, again, so NA, which is the neighborhood of the subset A, is equal to the union. the union of all NV for all vertex V in the subset A. Okay, to explain this definition, wait. So to explain about definition number 4, I give you example. Okay, let's say we are given graph G, which contains set V and set E. Alright, set V contains all the vertices and set E contains all the edges of the graph G. So suppose that the vertex V, the set for the vertex V, contains some vertices. We have V1, we have vertex V2, vertex V3, vertex V4, vertex V5, and vertex V6. Alright. Okay, and then we are given one set A, which is a subset of the set V, where the set A contains only two vertices, vertex V1 and vertex V2. Alright. Suppose that the vertex V1, okay, which belongs to the set A, is adjacent, okay, adjacent to vertex V3 and also vertex vertex V3, vertex V5, okay, and vertex V2, V2. What does it mean? That means in the graph G, so the vertex V1 is connected to the vertex V3, it is connected to vertex V5, and also it is connected to vertex V2. Alright. So that's why we call it as adjacent to V1. The vertex V1 is adjacent to V3, V2, and V5. Alright. So by using the notation N, which is the neighborhood of the vertex V1, it is a set that contains V2, V3, and V5. Alright. So finish with the vertex V1. Now we move to the second element of the subset A. We have vertex V2. Suppose the vertex V2 is adjacent to vertices V3 and V4. Okay, that means the vertex V2 is connected to vertex V3 and also vertex V4. So using the notation N, so the neighborhood of the vertex V2 contains V3 and V4. Alright. So now, we're back to the definition. Okay, we're back to the definition 4. Okay, so we have NA. Okay, NA is equal to the union of NV for all V belongs to the set A, which is subset of V. Alright, so what does it mean? So that means NA is equal to NV1 union NV2, because in the set A it contains vertex V1 and vertex V2. So the union of the neighborhood of the vertex V1 and the neighborhood of the vertex V2. So we combine together two different sets. Alright, so NV1 we have V2, 3, 5. Okay. Okay, and union with another set which contains V3 and V4. Okay, come from N V2. So we combine together. We have new set contains V2, V3, V4, and V5. Okay, so this is NA. Okay, so I hope you can understand the definition. The definition 4. Alright, the definition 4. Alright, so now we move to the next slide. So the following definition is useful to keep track of how many edges are incident. How many edges are incidents to a particular vertex. Okay, let's see the definition. In definition 5, the degree of a vertex in an undirected graph is the number of edges incident with it. The degree of a vertex in an undirected graph is the number of edges, representing the number of edges incident with that vertex, except that a loop at a vertex contributes twice. Again, a loop at a vertex contributes twice to the degree of that vertex. The degree of the vertex V is denoted by DEG in parentheses V. That means degree of the vertex V. So the degree of the vertex V is the number of edges that incident with the vertex V. Alright, so a vertex of degree 0. Okay, a vertex with degree 0, this kind of vertex is called as isolated. Okay, isolated because there is no other vertices connected to it. There is no edge comes to this vertex. It follows that an isolated vertex is not adjacent to any vertex. That's why we call it as isolated vertex. Alright, a vertex is pendant if and only if it has degree 1. Alright, if the degree is equal to 1, so this kind of vertex is called pendant. Consequently, a pendant vertex is adjacent to exactly one other vertex. Alright. I give you example. So let's consider this graph. So incident, the edge x incident to the vertices A and B. That's the terminology, the terms incident. Okay, the edge x incident to vertices A and B. Okay, we move to adjacent. The vertex B, okay, is adjacent to A, adjacent to C, and also adjacent to D. The vertex B. The vertex B is adjacent to A, adjacent to C, adjacent also to D. Means it is connected to A, it is connected to C, it is connected to D. Alright, so about A. So A is adjacent to B, A is adjacent to C. That's it. That's all. To B and to C. So about C. So C is adjacent to B and also adjacent to A. Right? And D is adjacent only to a single vertex, which is B. Alright? So that's for adjacent. So now we move to isolated. So as you can see, the vertex E doesn't have any other vertex connected to it. That's why we call it as isolated, because the degree of E is equal to 0. Okay, so E is isolated vertex. Then pendant. As you can see, D has only single vertex connected to it, which is B. That's why the degree of D equal to 1. So it is a pendant vertex. Alright. So I hope you can understand and you also can distinguish between these important terminologies in graph. Alright, so we move to the second example. Okay, the question, what are the degrees and what are the neighborhoods of vertices in the graph G as displayed in the following figure? So how to answer this kind of question? As you can read the question, this question asks you two different tasks. Okay, the first task is to identify the degrees of each vertex. Okay, vertex A, what is the degree? Vertex B, what is the degree? C, what is the degree? And so on until the vertex G. The second task, okay, the second task is to identify or to compute the neighborhood. So not to compute, to identify the neighborhood of the vertices in G. Okay, for the vertex A, what are the neighborhoods of this vertex and so on. All right, so let's see how to answer this question. So in this graph, for the vertex A, so we start one by one until from A until the vertex G. For the vertex A, the degree for the vertex A is 2. Why? Because it connected to two different vertices, B and F. So NA, okay, the neighborhood of the vertex A equal to B, F. Second one, for the vertex B, the degree for the vertex B equal to 4. Okay, because the neighborhood, the vertex B is connected to A, connected to F, connected to E, and also connected to C. Okay, and NB equal to ACEF. All right. For the vertex C, the degree C equal to 4, and the neighborhood of C contains, it is a set contains B, D, E, and F. And then for the vertex D, the degree is equal to 1. That means it is a pendant vertex. And the neighborhood of D is single vertex, which is C. And then for the E, the degree for the E is equal to 3. And the neighborhood of E, we have a B, C, and F. And then the degree of F equal to 4. Okay, equal to 4. So the neighborhood of F contains A, B, C, and E. The degree of, okay, be careful with the G. Yes, the degree is 0. Okay, because there is no other vertex connected to it. And the neighborhood of G equal to an empty set. Class, remember, an empty set is totally different with 0. Sometimes you confuse, I know. Okay, maybe some of you will just simply answer this question equal to 0. It's totally different with empty set because NG is a set. It is a set, so the answer also must be a set. Okay, so empty set is a set. That's why we use this notation. Alright, so be careful. Alright, so next, as usual, this is your favorite moment, I know. So waiting for quiz. So this is the quiz for your attendance. So I gave you about 5 minutes to complete your answer, and please email your answer to my email address. Okay, class, I give you 5 minutes to accomplish this question. Okay, so just like the given example in the previous slide, so this quiz also asks you two different tasks. Okay, the first task, okay, is about the degree, and the second task is the neighborhood. Okay, so just like the previous question, okay, in the previous slide, so the two tasks, degree and neighborhood. So how to answer this question? Okay. Okay, so let's discuss how to answer this question. So this is the solution. Okay, so to answer this question, you need to understand the definition of degree, also the definition of neighborhood. Okay, so recap. What is degree? So the degree of a vertex in an undirected graph is the number of edges. The number of edges incident with that vertex. Okay, and for a loop at a vertex contributes twice to the degree of the vertex. So as you can see, we have loop here. So be careful with that. So let's see how to answer this question. For the vertex A, the degree of the vertex A is equal to 4. Okay, let's count. We have how many edges? Okay, how many edges incident with the vertex A? We have edge 1, 2, 3, and 4. Alright, so that's why we have degree A equal to 4. So the neighborhood of A, we have B, we have D, also we have E. Although E is connected twice to A because this is a set, alright? Because this is a set, so just simply put E, okay? Single E here. No need to write E twice, right? Okay. The order is 4, but it contains only 3 vertices in the neighborhood of A. Alright, we move to B. So B, it has a loop. It has a loop. So a loop, as you can see in the definition 5, loop contributes twice to the degree of the vertex. So one loop contribute 2, alright, to the degree of B. So for the B, we have 1, edge 2, 3, 4, because we have loop, 5, and 6, because loop contributes 2. So we have the degree of B equal to 6, right? Equal to 6. So the neighborhood of B, we have A, okay? We have also B itself. We have B here, we have B here. That means we have a loop at the vertex B, right? So we have B, we have C, D, and also E. So for the vertex C, as you can see, it's very easy because there is only single edge. So the degree of C equal to 1. So there's single vertex connected to it, which is B, because that's why the neighborhood of C equal to B. For the vertex D, okay, vertex D, how many edges? 1, 2, 3, 4, and 5. 5 edges, so that's why the answer is 5. Okay, but there are only 3 vertices connected to it. We have A, we have E, we also have B. Although E is connected triple times, 1, 2, 3, but we only write E one time in the set and D. Okay, no need to write E, and E. Just single E here. Enough. Okay, so for the degree for the vertex E, the degree for the vertex E is equal to 6 because we have 1, 2, 3, 4, 5, and 6. 6 edges, okay, adjacent to this vertex E, and the neighborhood of the vertex E, we have A, we have B, and we have D, the vertices connected to E. Okay, I hope you can see the difference between degree and also the neighborhood, because in the previous example, as you can see, the degree is equal to the number of neighborhood. Okay, the degree of B 4, so there are 4 neighborhoods. So it's not necessarily always equal, as you can see in the quiz. All right, so we move to the next slide. So examining the degrees of vertices in a graph model can provide useful information about the model. So what do we get when we add the degrees of all the vertices of a graph G? Okay, we have a lot of vertices. So what happens if we add the degree of all these vertices in the graph G? Each edge contributes 2 to the sum of degrees of the vertices, because an edge is incident with exactly 2 or possibly equal vertices. Alright. What does it mean? That means, okay, this means that the sum of the degrees of the vertices is twice the number of edges, as provided in the theorem number 1. So theorem number 1 is called shaking theorem. Let G be a graph. Okay, let G be an undirected graph with K, where K is a natural number, it's a counting number of edges. Then 2K, okay, twice number of edges equal to the sum of the sum of the degree of all vertices in the vertex set V. Okay, let's say our vertex set contains V1, V2, V3. So 2k is equal to degree of V1 plus degree of V2 plus degree of V3. Okay, so this implies, okay, this applies even if multiple edges and loops are present. We can still use the same equation. All right. Now, the example number 3 is regarding the previous theorem. How many edges are there in a graph with 10 vertices, each of degree 6? Okay, each with degree 6. From the given questions, so we can get some information here. Okay, we have a graph G. Okay, we have graph G with set V and E. Okay, as usual. And then, where the set V contains how many vertices? Okay, we have 10 vertices. So we have V1, we have V2, all the way up to V10. Okay. Okay, so the question asks you how many edges? How many edges? So as given in the previous theorem, okay, we have 2k where k is the number of edges. Alright, k is the number of edges. So we have 2k equal to the sum of all degree. Okay, we sum of the degree of all vertices in the graph G. So in this case, we have 10 vertices, so that's why we have Vi, which belongs to the set V for all I equal to 1 up to 10. Okay, we have V1, V2 up to V10. So 2k is equal to summation of the degree Vi, where I is running from 1 up to 10. So the sum is equal to 60 because each vertex okay, because each vertex has degree 6. Okay, degree of V1 equal to 6. Degree of V2 also equal to 6, and up to degree of V10 also equal to 6. So 6 times 10, we have 60. Okay, we have 60. So now it's easy for us. Our task is to get k because k is representing the number of edges. Alright, so it's very easy to us to solve this equation for the unknown k. So unknown k is equal to 30. That means there are 30 edges. There are 30 edges in a graph with 10 vertices where each vertex has degree 6. The answer is k equal to 30. The handshaking theorem shows that the sum of the degree of the vertices of an undirected graph is even number. It's even number because it is equal to 2m. Oh, sorry, it's 2k actually. 2k where k can be any natural number. Alright, so now we consider theorem number 2. An undirected graph has an even number of vertices of odd degree. Okay, it is always even because it is equal to 2k, where k can be any natural number. So you can replace k with any natural number. It is always even. Doesn't matter if k is odd. Okay, no problem. It always even. Okay, definition number 6. When UV is an edge of the graph G with directed edge. Okay, directed edges. That means we know we have U and V. So we know U. Okay, we know that it starts from U and ends with V. Okay, the starting point is U and the ending point is V. So the vertex U is said to be adjacent to the vertex V. And the vertex V is said to be adjacent from the vertex U. Okay, it's different. U, for the vertex U, U is said to be adjacent to V. Adjacent to V, because in this ordered pair, we know that the starting point is U and the terminal point is V, or the ending point is V. So U is said to be adjacent to V, while V is said to be adjacent from U. Okay, so be careful with the terminology. Different terminology will give you different kind of graph. Okay, so the vertex U is called the initial vertex. The vertex U is called the initial vertex of UV, and the vertex V is called the terminal or the end vertex of U and V. Okay, that's why the order is important, because we know which one is the initial vertex, it is U, and we know which one is the terminal vertex, which is V. The initial vertex and terminal vertex of a loop are the same. Alright, so let's say in a particular graph we are given VU instead of UV. Okay, because this is an ordered pair. Okay, if we are given VU, so we know that the initial vertex is V and the terminal vertex is U. So that's how we say the order method, because it determines which one is come first before the other one. Alright, it's the order method, the order important. Because the edges in graphs with directed edges are ordered pairs, the definition of degree of a vertex can be refined to reflect the number of edges with this vertex as the initial vertex and as the terminal vertex. So previously, in the previous definition, okay, definition about the degree of vertex. Okay, so going back to definition number 5. So the degree, it is for undirected graph. So how about the degree of a vertex in a directed graph? Because definition 5 only deal with undirected graph. So let's see how to get the degree of a vertex in a directed graph. Okay, so in a graph with directed edges, that means for directed graph. In a graph with directed edges, the in degree of a vertex V, denoted by degree, we have minus sign as subscribe. Okay, subscription, we have a minus sign. Degree minus V is the number of edges with V as their terminal vertex. Okay, the vertex V as their terminal vertex. Again, in a graph with directed edges, means this is a directed graph. The in degree of a vertex V, denoted like this, we have small minus sign here, okay, is the number of edges with the vertex V as their terminal vertex. Again, we compute the number of edges, but this time we specify the number of edges where the vertex V is their terminal vertex. Alright, so other than in degree, we also have out degree. The out degree of the vertex V, denoted like this, we have a small addition sign there, okay, as superscript. Degree plus V is the number of edges with V as their initial vertex. Okay, as their initial vertex. So we have, for the single vertex V in a directed graph, so for a single vertex V, we have two different kind of degree. We have in degree. We also have out degree. Okay, for the in degree, it is denoted as small sign here, okay, minus sign. For the out degree, we have addition sign there, okay, small addition notation as a superscript. So we have in degree and out degree. Alright, so if you understand, you can distinguish between in degree and out degree. Note that a loop at a vertex contributes 1. A loop this time, a loop at a vertex contributes 1. Previously, in an undirected graph, a loop contributes twice. But for the directed graph, a loop at a vertex contributes 1 to both the in degree and out degree of this vertex. Okay. Example, find the in degree of each vertex in the graph G. Okay, with directed edges shown in the following figure. Okay, so as you can see, we have arrow here. That means this is a directed graph. This is a directed graph. So in this question, the question asks you to find the in degree of each vertex. That means we need to find the in degree of the vertex A, the in degree of the vertex B, the in degree of the vertex C up to vertex F, the in degree of the vertex F. Okay, let's see how to answer this question. Okay, so in the in degree in the graph G are as the following. Okay, for the vertex A, so we have how many in degree? So to find the in degree, we just simply refer to the direction of the arrow. Just count the number of arrow comes to A. We have 1, 2. Okay, so this arrow pointing to A. So the in degree of A equal to 2. How about B? Okay, let's see how many arrows pointing to B. We have 1, we have 2. So the in degree of B equal to 2. How about C? C, we have loop also. Okay, so previously in undirected graph, loop equal to 2, but this time loop equal to 1. So we have 1. Okay, and then we have another one, and then we have another one. Okay, 3 arrows pointing to C. So the in degree of C equal to 3. So how about D? Where is D? This is D. So how many arrows pointing to D? We have 1, we have 2. Alright, so the in degree of D equal to 2. So how about E? So E, we also have loop. So we have 1. And then the second one is here, 2. And the third one is here. Okay, 3. So the in degree of E equal to 3. So how about the in degree of F? So it is isolated. Okay, isolated. Tidak dikawan ini. So F is isolated vertex. So the in degree of F equal to 0. Alright. Senang kan? It's easy. Okay. Move. Oh, again. Okay, your favorite moment. The quiz. So again, I gave you about 5 minutes. Okay, I give you about 5 minutes. Please answer this question. So previously, I asked you about the in degree. So this time, I asked you about the out degree of each vertex in the graph G. Okay, again, I give you a directed graph. Actually, the same graph as the previous one. But this time, I ask you to find the out degree of each vertex. So I think it's very easy for you to answer this question. Alright, so I give you about 5 minutes and then submit your answer to my email. Okay, go. Okay, so now it's time to discuss this the answer for this quiz. Okay, let's see how to answer this question. Alright, so this is the solution. So the notation is we have small addition sign here. Okay, that means it is an out degree. So previously I asked you to count the number of arrow pointing to each vertex. So now we need to count the number of arrows that pointing out from a vertex. Okay, that's why we call it as out degree. Okay, for example, A. How many arrows pointing out from A? We have 1, we have 2, we have 3. And another one, don't forget about the loop, we have 4. So the out degree of A equal to 4. The out degree of B, where is B? Yeah, B. So how many arrows pointing outside B? Pointing out from B? We have 1. Yeah, only 1, because this 2 arrows comes to B. Okay, these 2 arrows come to B, so our interest is only to count the number of arrow going out from B. So only 1. How about the out degree of C? Where is C? This is C. First of all, we have loop. So number 1 is loop. Number 2 is this arrow. Okay, this edge. So we have 2. And yeah, only 2. For C, same goes with D. We have 1 and we have 2. Okay, only 2 edges going out from D. And for E, we have 1. We have loop number 2, and we also have this number 3. So the degree of equal to 3. And again, F, which is yalah, yang tidak dikawan ini, F. So the degree of F, because F is isolated, so the in degree and out degree of F is always equal to 0. Okay, because it is an isolated vertex. Alright. Because each edge has an initial vertex and a terminal vertex. Each edge means the line connecting to at least 2 vertex. Okay, because each edge has initial and a terminal vertex. Okay, this is for U and V lah. Okay, start from U to V. Alright. The sum of the in degree and the sum of the out degree of all vertices in a graph with directed edges, means for directed graph, are the same. Where both of these sums are the number of edges in the graph, as shown in the theorem number 3. Suppose G be a graph, okay, with set V and set E, okay, with directed edges. Then, okay, the sum of the in degree of the vertex V for all V in this vertex set V equal to the sum of the out degree of V for all vertices V in the vertex V. Okay, and these summations actually, each summation equal to the cardinality of the set E. The cardinality means the number of entries, the number of members of the set E. They are same, they are equal. Okay. Alright. There are many properties of a graph with directed edges that do not depend on the direction of its edges. Okay, so consequently, it is often useful to ignore these directions. So the undirected graph that results from ignoring directions of edges is called the underlying undirected graph. So basically, underlying undirected graph is originally a directed graph, but we ignore the direction, so we have a special name for this kind of graph. We call this directed graph as underlying undirected graph. So basically, it is originally a directed graph because we ignore the directions. We call it as underlying undirected graph. Alright, so now we move to the next topic, which is about some special simple graphs. We have some different special graphs. Okay, so the first graph is what we call as complete graph. So what is complete graph? A complete graph of n vertices. Where n is greater than or equal to 1, denoted by kn. Okay, so that means we have k1, we have k2, okay, and so on. Alright, for n greater than or equal to 1, and so on. So it is a simple graph that contains exactly one edge between each pair of distinct vertices. Okay, again, contains exactly one edge between each pair of distinct vertices. So this kind of graph is what we call as complete graph. A simple graph for which there is at least one pair of distinct vertices not connected by an edge is called non-complete. Okay, means non-complete graph. So I'll give you some example to illustrate about the complete graph. So let's say we have n equal to 1 up to 6. So we have 6 different complete graphs displayed in this figure. So for K1, of course, we only have single vertex. For the K2, we have 2 different vertices connected by single edge. Right? Single edge. And then for K3, we have 3 vertices. 1, 2, 3. Okay, and for 2 different vertices connected by single edge. Alright, single edge, single edge. Alright. And then for K4, we have 4 different edges. 4 different vertices. 1, 2, 3, and 4. And for each 2 different vertices connected by single edge. Alright, single edge. Alright, that's why we call it as complete graph. Okay, so we also have K5 for n equal to 5. Also have K6 for n equal to 6. Okay, so finish with the complete graph. We move to cycles. A cycle denoted by Cn, where n is representing the vertices. So this time the n is greater than or equal to 3. Means the smallest n for the cycle is 3. Alright, so we have C3, C4, and so on. Alright, so a cycle Cn consists of n vertices. Okay, contains n vertices, and edge E1. Okay, and edge E1 contains V1, V2. Edge V2 contains V2, V3, and up to edge En-1 equal to Vn-1 Vn. And for the edge En, we have Vn, V1. Okay, so to make it clear, I give you example. Let's say our n is equal to 4 lah. Okay, it's equal to 4. Okay, so for the cycle C4, alright, C4. So how many edges? How many vertices? For the cycle C4, vertices V, we have vertex V1, V2, V3, and V4. Alright, for edges, for vertices. So how about the edge? For the edge E1, we have vertex V1, V2. For the edge E2, we have vertex V2, V3. Okay. For the edge E3, we have V3, V4. And the last one, the final one, we have E4 contains V4 and V1. Okay, Vn, V1. So our n equal to 4, so it ended with E4 equal to V4, V1. So that is C4, cycle C4. So I give you some examples. Cycle V3, C4, C5, and C6 as shown in this figure. So if the graph for the cycle C3, alright, cycle C4, cycle C5, and cycle C6. Okay, so this is our C4. For example, we have vector V1, vertex V2, vertex V3, and vertex V4. So here we have the edge E1 connecting V1 and V2, V1 and V2. We have edge E2 connecting V2 and V3. Okay, connecting V2 and V3. We have edge E3 connecting V3 and V4, and we have edge VE4, which is connecting V4 back to V1. So we have E4 here. All right. So we have example for cycles. Now we move to wheels. A wheel denoted by capital WN can be obtained. It can be obtained by adding an additional vertex, single additional vertex to a cycle. Okay, because that means Cn, we add additional one vertex, so it becomes Wn, wheels, where n is greater than or equal to 3. And connect this new vertex to each of the n vertices in Cn by new edges. Okay, so give you example. Previously we have cycle C4. So if you have additional vertex to it, single additional vertex, it becomes a wheel 4. Okay, so this is the example for the wheel 4. We have additional the original vertex V1, V2, V3, and V4. So for the wheel W4, we have additional vertex. That means one vertex we denote as V5. Okay, and another condition is we need to connect this new vertex to all original vertex in this cycle. Okay, that it becomes a wheel. Although there are 5 vertices, but we have W4 because 4 is representing the number of original edges in the cycle Cn. Right? Alright. So finish with wheels. We move to cubes. So we have n cubes. So what is cube? An n-dimensional hypercube, or simply known as n cube, denoted by Qn. It is a graph that has vertices representing the 2n bit strings of length n. 2n bit strings of length n. Okay, bit, we know bit, we have 0 and 1. Alright, two vertices are adjacent. Okay, are adjacent to one and another if and only if the bit strings that they represent differ in exactly one bit position. So I give you example of n cubes. So for n equal to 1, we have Q1. Okay, Q1 means we have two vertices. Okay, 1 and 2, and each vertex have their bit representation. So we have 0 and 1. So this is for Q2. Okay, we have how many vertices? We have 1, 2, 3, and 4 vertices. Okay, 4 vertices. So each vertex has 2 bit. Okay, 2 bit. Okay, bit strings of length n, because this is Q2, so the length is 2. Alright, because n equal to 2, so we have 2n, n equal to 2, so 2 equal to 4. There are 4 bit strings. We have 1, 2, 3, and 4. Alright, so each bit strings, the length is n equal to 2. So the length is 2, 1, 2, 1, 2, 1, 2, 1, 2. Alright, so just following the definition. Alright, so I think we finished with the cube. So now we move to bipartite graph. So what is bipartite graph? So in definition 8, okay, a simple graph G is called bipartite. If its vertex set, which is capital V, can be partitioned into two disjoint sets, V1 and V2. The original set is V. Now we partition, means we divide. Okay, we separate to two different sets denoted by capital V1 and capital V2, such that every edge in the graph connects a vertex in V1 and a vertex in V2. Okay, again, A simple graph G is called bipartite if its vertex set capital V can be partitioned into two disjoint. Okay, so V1 and V2 are another two sets, and these two sets, the first condition is these two sets must, okay, so these two sets are disjoints. That means the intersection between V1 and V2 is equal to 0. No, it's equal to an empty set because they are disjoint sets. There is no common element between these two sets. That's the first condition. The second condition, such that every edge in the graph connects a vertex in V1, okay, connects one vertex in V1 and one vertex in V2. Every edge in the graph connects one vertex in V1 and one vertex in V2. Okay, let's say we have two. V1. What else? Okay, we use different notation lah for edge. Okay, let's say A and B. Okay, two vertices, and we have H1, E1. So this edge is connecting A and B. Okay, where A comes from the set V1 and B comes from the set V2. That's the second condition. So that no edge in G connects either two vertices in V1 or connects two vertices in V2. When this condition holds, so the pair of these two sets, V1 and V2, is called a bipartition of the vertex set V of G. Alright, so there are two conditions. The first conditions, these two sets V1 and V2 must be disjoint sets. That means the intersection between these two sets are the intersection equal to an empty set. The second condition, every means all edges. Every edge in the graph G connects one vertex in V1 and one vertex in V2. Then we call the graph G as bipartite. Okay, as usual, I give you example. Consider the figure of C6. C6 means we have a cycle. Cycle 6 means the cycle C6 means n, which is the vertices equal to 6. There are 6 different vertices. So in this graph, okay, there are 3 vertices in the set V1. Okay, back. So we have C6, okay, cycle. That means the vertex set V, the original vertex set, contains V1, V2, V3, V4, V5, and V6. Why? Because n is equal to 6. That means there are 6 different vertices. So we denote by V1 up to V6. This is the original vertex set V. And then we divide or we partition this set V into two different sets, V1 and V2, where these two different sets are disjoint. As you can see, there is no common element in both sets. There is no common elements. Semua elemen berbeza. Right? And every edge of C6 connects a vertex in V1. Okay? And a vertex in V2. For example, this edge, denoted by E1. Okay? So it connects vertex V1 and vertex V2. Vertex V1 comes from vertex V1. Vertex V2 comes from the set V2. Same goes with the second edge, E2. E2 also connecting one vertex in the set V1 and another vertex from the set V2. So it happens to all edges. Okay? This edge, this one also same, this one same, and this one same. Okay, every edges in this graph connecting one vertex from the set V1 with another vertex in the set V2. So this graph C6 is bipartite. Okay, it is a bipartite graph. So maybe in exam the question is I give you one graph and please determine whether the given graph is bipartite or not. So later I'll show you how to actually answer that kind of question. Okay, this is just example. Never mind. Later on I'll show you how to answer this kind of question. Okay, to determine or to identify whether the given graph is bipartite or not. Okay, we move to example number 6. Again, the same question. Is the graph K3 bipartite? Okay, it is a complete graph with n equal to 3. That means we have 3 different vertices. V1, V2, V3. Alright? The conclusion is K3 is not bipartite. Okay, why? Note that if the vertex set of K3 is divided into 2 disjoint sets, okay, because we only have 3 vertices. Okay, so the original vertex set contains V1, V2, V3. Okay, so if the vertex set of K3 is divided into 2 disjoint sets, one of the 2 sets must contain 2 vertices. Because there are only 3 vertices, so if we divide to V1 and V2, one of these 2 sets must contain 2 vertices. Must contains 2 vertices, either V1 or V2. If the graph is bipartite, these 2 vertices could not be connected by an edge. But in K3, each vertex is connected to every other vertex by an edge. So that's why the conclusion is K3 is not bipartite. So don't worry, later I'll give you the way how to determine the given graph is bipartite or not. I show you easier way how to answer this kind of question. Okay, example number 7. Are the graphs G and H displayed below bipartite? Okay, is G is bipartite? Is H is bipartite? Okay, so the final answer for this questions is the conclusion whether G is bipartite or not bipartite, or NH is bipartite or H is not bipartite. So that is the answer for this kind of question. You must provide the conclusion, your conclusion. But before you come out with the conclusions, you need to provide the way how you come out with that conclusion. Okay, provide the steps, provide the methods before you can come out with the conclusion, and you can get full mark for this kind of question. Okay, so this is the solution. The graph G is bipartite because its vertex set is the union of 2 disjoint sets. The first set, V1, okay, originally we have V, the original set of vertex, we have A, B, C, D, E, F, and G. Okay, and then divided into 2 disjoint sets. The first set contains A, B, C, and the second set is containing C, E, F, and G. As you can see, there is no common element between these 2 sets. So these 2 sets are disjoint. Okay. So we fulfill the first condition. Okay, and then each edge, every edge connect a vertex in one of these subsets to a vertex in the other subset. Okay, I give you example. Okay, for the vertex A, okay, it connected to G, it connected to F, it connected to E, it also connected to C. Okay, it connects from A, it connects to C. To C, it is also connected to E, it is also connected to F, it is also connected to G. So from one set connected to the other set. Same goes with B and also same goes with D. Alright, so that's why we conclude that this graph is bipartite. Note that for G to be bipartite, it is not necessary that every vertex in ABC be adjacent to every vertex in CEFG. For example, B and G are not connected. Okay, B is not connected to G. Okay, not necessary must connect to all the 4 entries in V2. Okay, for example, B, it only connects to F, E, and C, but it is not adjacent with G. Doesn't matter, it is still bipartite. So the question is how to actually easily answer this kind of question. How to identify whether the given graph is bipartite or not. Okay, so I give you the another way by using colors. Okay, by using 2 different colors. Okay, for example, we start with a vertex A, right? Vertex A. For the vertex A, we put or we color this vertex with one color. Okay, we just need to use 2 different colors. So for in this example, we use red and we also use blue color. For the original vertex, because we consider vertex A, for the original vertex A, we color this vertex as red color. Okay, like this, red color. And then the second step is for all vertices adjacent with this vertex, we call as color blue. Okay, for example, this vertex A connected to G, so we color G with blue color. The vertex A connected with F, so we color F with blue color. Okay, and then the vertex A also adjacent with E, so we color E with blue color. So the vertex A also connected to C, so we put the vertex C with blue color. Okay, so finish with A. Now we move to B now. Okay, because we consider the vertex B, so we put red color on B. And then as usual, as just like the previous step for A, we color all the vertices connected to B with blue color. Okay, blue is connected to F. Yes, it is already in blue. Then we can proceed to the next vertex. B also connected to E. E is already in blue color. Then we proceed to next vertex. B is connected to C. C is already in blue color. Okay, so we cover all the vertices without any changes, without any change in the color. For the other vertices, G still blue, F still blue, E still blue, and C also still blue. Alright, so we move to the next vertex, which is D. Okay, so we color D as red color also. Okay, and then D is connected to C. C is already in blue color. And then D connected with G. So G still is already in blue color. D also connected to F. F is already in blue color. D also connected with E. E is already in blue color. Now we cover all the vertices with different colors. Okay, with different colors. And then we don't change any color that we already give to that vertex. For example, G. We never change the color blue of the vertex G. Same goes with F. We also never change the color for the F. E also, and also for all vertices they maintain with their own color. So each vertex can be assigned with single color. Okay, single color. So that's why all the same colors we put in single set. A, B, D. And the other color blue we put in another set. We have C, D, E, F, and G. Exactly same with the previous answer. Okay, we have 2 different sets. All right. So as you can see, there is no common element here. There's no common element here. So these 2 sets are disjoint. Okay. So there are the given graph G is bipartite. That's our conclusion. Okay. Okay. So how about the second one, H? Second one, H. So in this graph, again, we use the same way as we answered the previous one. We're using color, two different colors, blue and red. We start with A. Because we start with A, we put red color on A. So we put colors on all vertices connected to A by blue color. For example, F, blue, E also blue, and then B also blue. There is no other vertices. There is no other vertex connected to A other than these three vertices. Okay. Next, we move to okay, so here as you can see, for example, the vertex F, it connected to two different colors. It connected to red and also it connected to blue. Okay, that means this vertex is connected to two different sets. A is, let's say it comes from the set V1, B connects to the vertex V2. So this vertex F connected to two different color. So we just no need to continue to other vertex. We can conclude that H is not bipartite. Okay, because its vertex set cannot be partitioned into two subsets, so that H do not connect two vertices from the same subset. It differs with the previous example. As you can see, G is connected to red, G is connected to red, F is connected to red, F is connected to red, F also connected to red, E is connected to red, E is connected to red, E also connected to red. Okay, same goes with B. B is connected to blue, and to blue. Only blue to red, blue to red, blue to red, and also red to blue, red to blue, red to blue. Alright, but in this case, we have blue to red, blue to blue. So we can come out with the conclusion that H is not bipartite. Alright, if we use the color method. Okay, if you use color method. From F, as we can see, it connected to red, it also connected to blue. Alright, so automatically we can conclude that the graph H is not bipartite. But please provide a proper reason. Alright, because its vertex set cannot be partitioned into two subsets so that edges do not connect two vertices from the same subset. Actually, the color method comes from this theorem. Okay, theorem number 4. A simple graph is bipartite. Okay, is bipartite if and only if it is possible to assign one of two different colors. For example, in previous example, we use red and blue to each vertex of the graph so that no two adjacent vertices are assigned to the same color. Alright. So complete bipartite graph, a complete bipartite graph. Previously, for the complete graph, we have Kn. So for that, this notation is only for the simple complete graph. So but for the complete bipartite graph, we have Kmn. Okay, we have additional value here. We have m. Okay, so Kmn is a graph that has its vertex set partitioned. The vertex set V partitioned into two subsets of m and n vertices. Okay, it is the original vertex set divided into two different sets, V1 and V2, where the subset V1 contains m vertices, okay, equal to m, and the subset V2 contains n vertices, so the cardinality equal to n, respectively, with an edge between two vertices if and only if one vertex is in the first subset and the other vertex is the second subset. The complete bipartite graphs for K23, K33, K35, and K26 are displayed in the following figure. As you can see, for K23, that means the vertex v1, okay, set the cardinality is equal to 2, and for the vertex set v2, the cardinality is equal to 3, as you can see here. So we have 2 here, okay, comes from the set v1. We have 3 vertices here, which is come for the vertex v2. Okay, that's why the cardinality is equal to 2 here, and this one is equal to 3. Okay, m equal to 2, n equal to 3. Okay, this is a bipartite graph, complete bipartite graph. So for this one, okay, in v1 we have 3, okay, 3 vertices. For the another set v2, the cardinality is equal to 3 because we have m equal to 3, n equal to 3. So this is the complete bipartite graph for m equal to 3 and n equal to 3. So here we have 3, 5, and we have 2, 1, 2, 3, 4, 2, 6. Okay, 2, 6. All right. So theorem. Okay, so that's all for the first part of this lecture for the chapter number 7. So later on, we'll continue to the second part of this chapter. Okay, thank you, class.